This demonstration is about X-ray crystallography, which is a technique scientists use to study the atomic structure of solid materials, like crystals. So in a crystal, atoms are arranged in a periodic pattern, such as this. In this demonstration, the ping pong balls are the atoms, and the springs are the forces between the atoms. In order to see the atomic structure of a crystal, scientists can't use regular light. They need to use X-rays, which are very high-frequency light. And with X-rays, they're able to peer inside and see how the atoms are arranged. So in this demonstration, we're going to be looking at the structure of atoms in solid objects. So in this first one, if you have a glass container like this and you have some spare balls you can fill it with, you can demonstrate why atoms tend to form into nice repeating orderly patterns. So in this case, we start off with the balls kind of all piled up on each other with no real pattern there. But if we add a little bit of energy by shaking it, then the balls will naturally fall into this nice ordered pattern. And so this sort of close packing structure arises because the balls all have more or less the same shape, and when you add energy into the system, it's able to relax to this lowest energy state where the balls are all nice and ordered. Since atoms are so small, we can't actually see them with our eyes under normal conditions. And so at the beginning, we're going to cover the crystal model with this black cloth, and students are going to have to use X-rays, which are represented by these photons, which are two ping pong balls connected by a spring, in order to throw them at the model from different angles and try to determine, based on how the photons scatter off the crystal, what the underlying atomic structure is. So one person will be holding the photons and they throw it at the model, the other person marks where it lands and measures using a ruler how far from the model the ball flew. And then they record that distance along with the angle they threw it at. So in that case, I was throwing it from 240 degrees, and then partners can rotate the model. So this time I'll do it from the 270 degree. That one didn't really bounce anywhere, so if it just sort of lands on the photon model, that should be a zero distance. But that one jumped off, so measure the distance, and in the table record it under 270 degrees. And then partners can switch off and just keep rotating. Yeah, so in that case, it went really far, so I was throwing it from 210 degrees, and it bounced very far away from the model. So that was an example of constructive interference, where the photons were lined up directly with the positions of the atoms under the sheet. So students should rotate the model, throw from many different angles, and see which ones lead to the largest scattering distances, and try to determine what the shape of the crystal atoms underneath the sheet are from their data, and compare hypotheses with different groups. Once students have finished comparing their hypotheses, you can uncover the crystal models and they can see how the atoms underneath the sheet are actually arranged. It doesn't matter what shape you chose to set it up as. We chose this one where atoms along this axis are separated farther from atoms in this direction. We chose to do that because the photons can have a single length, so we chose the length to match these two atoms, but it's off-axis for these two, so it'll only scatter strongly when students throw the photons from this direction. And we hope that helps them figure out what the shape of the lattice is. But so once you uncover it, there's one more thing you can do, which is to demonstrate sound waves. So sound waves in a lattice are formed by the atoms vibrating, and that's why we chose to couple our atoms, the ping pong balls, by springs. So whenever you give one of them a little flick, all the atoms in the crystal will vibrate because they're all connected to each other with the springs. So in order to visualize this motion, because as you can see it's kind of small, we also added a mirror to the very center, and we're shining a laser on it from over here. So the laser bounces off the mirror and is hitting the wall. So as the students are tapping on the balls and moving them around, sound waves will propagate through the crystal, and the ping pong balls, or the atoms, will bounce around, and the mirror will be moved up and down and back and forth at different frequencies. And as a result, the laser, which is bouncing off the mirror, will trace out these very interesting patterns. So in addition to having students drive the model by flicking the balls themselves, you can also drive it using a speaker. So in this case, we've taped down a small speaker that's pressed right up against one of the balls in the crystal. So if we play a pure note over the speaker, the atoms will all be driven in sync with one another, as you can see. Laser won't create a visible pattern. And if we continue changing the frequency, then we can find all the different notes that are resonant with the crystal model and look at all of these interesting Lisa Drew patterns.